Thanks to Brilliant for sponsoring today's video.
In a basic calculus class, students learn what the first derivative and the second derivative say about the shape of a curve, but you never really think about what the third derivative says about the shape of a curve, and that's what we want to explore today. And this is from a great article that I found in the Math Gazette. You can find it with this information down here. So let's first review what the first and the second derivative say, and then we'll move into looking at what the third derivative says. So the first derivative, y prime, if we have the curve y equals f of x, is the slope of the tangent, or really just the slope of the curve at a point. But we could also think about that as how far the curve is from being a constant function at that point, of course. And then, well, the second derivative in a first semester calculus class really just tells you the concavity. Is it concave up or concave down? But if you push a little bit further, you can see that the second derivative is related to this notion of curvature. And you generally learn about curvature, at least in the US, in a third semester calculus class. And for a curve of the form y equals f of x, the curvature is the second derivative over 1 plus the first derivative squared all to the 3/2 power. So let's notice that the second derivative here has a really important part to play in this notion of curvature. And then we can also think about the curvature as how far the curve is from being a straight line. And that's because the curvature of a line using this calculation is pretty obviously equal to 0 because the second derivative of an equation of a line is 0. Furthermore, this thing up here that we already talked about makes sense because the slope of a constant function is always 0. And so that means a constant function is maybe distance 0 away from being a constant function, and a line is distance 0 away from being a line. So these two yellow comments kind of make sense in those terms. So now let's start looking at what the third derivative says, and I've got the following maybe sketch that will help guide us through this situation. So I've got my coordinate axes and my curve y equals f of x here. And I'd like to observe that we can always transform a curve so that it goes to the origin. So we know that f of 0 is 0. And then here we're going to assume that f double prime of 0 is non-zero. And well, let's see. In general, it's not f double prime of 0, it's f double prime of whatever point that we started at that we transformed to 0. So that's how this would be done more generally. So the way that you could do what we're doing today back to, a general point is just to transform away from 0 however you want to. Okay, cool. So now let's observe that we've got a horizontal tangent at the origin here. And also I've written this, or I've drawn this graph in a way that there's this asymmetry about the vertical axis. And before we really dive into this, the way that I've drawn it here, this horizontal axis, this x-axis, is really better thought of as the tangent line. So I'll just say this is the tangent to y equals f of x at x equals 0. X equals c if we had it more general, but we've transformed away. And then, well, this vertical axis is the normal line. And so, well, what's the normal line? Well, it's simply the line that's perpendicular to the tangent, or orthogonal to the tangent, if you will, and it goes through the same point. So now, along the path to constructing this geometric notion of the third derivative, what we'll do is find a chord which is parallel to the tangent line. In other words, in this case, it's going to be parallel to the x-axis. And well, in order to have a chord, we must have two intersection points with the curve. Now, in our drawing, we pretty clearly have two intersections points with the curve, but we'll always be guaranteed to have two intersection points with the curve near our point of interest because we're doing this assumption here that the second derivative is non-zero, and thus, well, we're not changing concavity at this point. Okay, so here, let's draw this. Maybe we'll take this point right here, and then we want it to be horizontal in this case, parallel to the tangent. So perhaps we'll take this point right here. Okay, so that looks pretty close to being parallel to the tangent. Now, what we'll do from here is take the midpoint of this chord. So let's see, the midpoint of this chord will be right about here. Okay, so there's our midpoint. And then what do we want to do from there? So from there, I'm going to take the line that's defined by the origin, and it's defined by this midpoint. So let's draw that right here. Okay, so there's our line defined by those 2 points. And now I'm going to go ahead and put some names to some of these things. So this midpoint right here, I'm going to say it has the following coordinates. So I'll call this A epsilon, comma, B epsilon. And so, well, what is epsilon? Well, let's define that down here. So epsilon is going to be the distance from the chord to the tangent line. But you always take the distance along a perpendicular. So, well, it would be that distance right there, which is about one of my index fingers. And now, well, notice that if we take the limit as epsilon goes to 0, that's going to push this chord all the way down here. And notice that A epsilon, B epsilon will approach the origin. But maybe more importantly, A epsilon, B epsilon will approach whatever point we're constructing the tangent line at if we were doing this prior to our shifting. Okay, cool. So now we've got that point at A epsilon, B epsilon. Then notice that there's also something kind of obvious to look at here, and that would be this angle. Okay, so let's maybe call this angle theta sub epsilon. And notice that that angle is going to change kind of depending on the asymmetry of the curve as we let epsilon approach 0. But that angle, you know, most likely will not be 0. And in this case, I think you can tell that it's not going to be 0 because we've got a steeper curvature over here and like a maybe more gentle curvature over there. Okay, and that brings us to the definition of, well, this word down here, which is inside of the title of this article, which is the aberrancy. So let's maybe write that up here. So let's define the aberrancy of the curve y equals f of x at the point x equals c, which in our case is like kind of obviously equal to 0, as the following limit. And that's going to be the limit as epsilon goes to 0 from above of the tangent of theta epsilon. So we don't explicitly need to know what the limit of that angle is. We need to know what the limit of the tangent of that angle is. You know, and perhaps we could give this some notation if we wanted to. Maybe we could say this is A of C, to say the point C. Now, let's observe that in our case, since we've got a horizontal tangent line and a vertical normal line, that means that the tangent of theta epsilon is simply B epsilon over A epsilon. But that's generally not the case. But even though that's generally not the case, that's still going to be a limit that's interesting to look at. So let's maybe put also, we'll define the following quantity. And this will be S sub C. And well, C is equal to 0 in this case, but I'll leave it as S sub C so it's more general. And that's going to be the limit as epsilon goes to 0 from above of B epsilon over A epsilon. And like I said, since this B over A is the tangent of theta just by the definition of tangent, in the case that you've got a horizontal tangent, and a vertical normal, then that means that those two limits are the same. But that's generally not the case. And I'm not going to work through the details on this. This just involves like some basic trigonometric identities, but I will put it as a note here. And that would be the maybe translation between the aberrancy and then this SC type object. And it goes like this. So A of C can be calculated as 1 over m minus S sub C over 1 minus S sub C over m. And you might say, well, what is m here? Well, m is the slope of the tangent at C, which, in our case is 0 again. And now I'm going to make a couple of observations which will allow us to maybe not fill in this object over here for aberrancy, but will allow us to fill in this like little remark here. So let's maybe see the following two facts. And the first is that the aberrancy is invariant under rotation. Well, I think that's pretty clear because if you rotated this whole situation, in particular, you rotate the curve, then you're going to rotate the tangent, you're going to rotate the normal, and you're going to necessarily rotate the blue line as well. And then the next thing, which is maybe the most important towards getting this kind of idea over here, is the aberrancy of a circle is in fact 0. And well, you can see that just by drawing a picture. I think you can do this via calculations as well fairly easily. But let's say we've got two perpendicular lines here. One will end up being the normal of the circle and one will end up being the tangent of the circle. Let's say maybe this horizontal line is the tangent of a circle. So we've got a circle right there. That's, fairly close enough to being circular. Now, if you draw one of these chords like we had done before, so there would be a chord, but then let's look at this midpoint here. This midpoint is always going to be along the normal line. But if that midpoint is always going to be along the normal line, then that means your theta epsilon angle will always be equal to 0, which means this limit up here will always be 0. But that means that the aberrancy of a circle is 0. But looking at this over here, that means that this notion of aberrancy, which we will get a formula for, is really how far a curve is from being a circle. Okay, so keeping all of this in mind, let's maybe see if we can produce a formula like these two for the aberrancy of a plane curve.
Hey there, I'd like to take a minute to talk about today's sponsor, Brilliant.org. Brilliant is a super interactive learning platform designed to get you hands-on with concepts in math, science, and computer science. Their courses are all about doing. So instead of just reading a bunch of theory, you're actually solving real problems step by step. You're learning by experiencing it, which, trust me, makes it so much easier to remember. Content is designed by an award-winning team from MIT, Caltech, Duke, Microsoft, Google, and more. Brilliant is also something that you can take with you on the go. The mobile app makes it easy to pick the time that works for you. Check out their course library. They have new courses on data science that are perfect for learners at any level to start. They also have a full suite of new content covering data visualization, algorithms, regression models, and more. But we're scientists here, so don't take my word for it. You should test it for yourself. A subscription would also make a great gift for the upcoming holiday season. Treat yourself to a unique hands-on experience by going to brilliant.org/michaelpenn for a 30-day free trial and 20% off your annual subscription. Thanks once again to Brilliant for sponsoring today's video.
So like we ended on the last board, we see that the aberrancy seems to be how far a curve is from being a circle. Now we're going to come up with a formula for this in the special case that our function is a polynomial. And well, how far is this from being something general? Well, probably not as far as you might think, because if you have a nice function, I'll let you maybe figure out what nice means in this setup, then it's a sequence of polynomials. So you could maybe think of the aberrancy as the limit of the sequence of the polynomials that converges to our function, or something like that. But doing it for a polynomial will at least get us a formula like one of these over here. Okay, so here's our setup. We've got, like I said, a polynomial, cn x to the n plus cn minus 1 x to the n minus 1, all the way down to c1x. So that means it's been pre-shifted so that it goes through the origin. Let's also assume that c2 is bigger than 0. Just for the sake of argument, you could repeat this when c2 is less than 0. That's the second derivative in this case. Okay, so now I've got a mock-up of my curve right here. And now I'm going to draw a tangent at the origin. So notice the tangent is not horizontal in this case. So we're already like a little bit more general than we were before. Okay, so there's our tangent. And then next up what we're going to do is find, let's see, we needed to find a chord that is parallel to that tangent. So here we'll just draw something like that. Okay, cool. And then I'm not going to really fill in the other parts because, well, it'll get pretty messy, but they're going to be essentially like we had before. Okay, so now let's collect some data over here. And let's observe that the equation of the tangent line at x equals 0 is pretty clearly equal to y equals c1 of x. And then next up, we can see that the equation of this chord also has a fairly simple, maybe formula. And that goes like this. So equation of the chord is, well, it's going to be y equals c1 times x plus epsilon. So it has to be parallel to the tangent, so it needs the same slope, and then we'll just shift it up by epsilon. And now we're going to define two other numbers. So let's say that L epsilon is the largest negative intersection of the line defining this chord and our curve. But notice our picture is making that happen already. Notice that if we were to extend this chord into a line, it would intersect again over here somewhere, and again up here somewhere. But L epsilon, that's the largest negative intersection in our picture. But notice we may have like kind of a lot of intersection points given that we've got a high degree curve. So it's important to set it so that we have this largest negative intersection point. And then as we'll see, this R epsilon will be the smallest positive intersection of those two as well. So let's get those over here. So that means that would make this point right here L epsilon, and then this point right here R epsilon. But now we can get full coordinates for these. Notice this L epsilon and R epsilon are just x coordinates. So notice L epsilon is going to be paired with, let's see, it's going to be something like C times L epsilon plus epsilon, just given the fact that it is a point on the chord. And then the full coordinate for the point associated to R epsilon will be R epsilon and then C R epsilon plus epsilon for, well, essentially the same reason. Okay, and then, oh, that should have been a C1 L epsilon and a C1 R epsilon, just given the fact that we have a C1 there. But now let's use our notation from before, our A epsilon, B epsilon, which has got to be the midpoint of these two. But it's pretty easy to calculate the midpoint. Observe that we get L epsilon plus R epsilon over 2 for the x coordinate. And for the y coordinate, we have C times, or C1 times L epsilon plus R epsilon over 2, and then plus, well, observe that's going to be 2 epsilon over 2. In other words, it's going to be epsilon. Okay, cool. But now from here, we can calculate that SC object. And what's that going to be for us? Well, I'm going to write it as S0, and that's going to be the limit as epsilon goes to 0 of B epsilon over A epsilon, which ends up being the limit as epsilon goes to 0, I guess I should say from above here, of, now after doing a bit of calculation, which is pretty straightforward, we're going to get something like this. So C1 plus 2 epsilon over L epsilon plus R epsilon. But notice as epsilon goes to 0, the numerator of the fraction in there goes to 0. But then L epsilon and R epsilon will also go to 0, kind of obviously just based on where this chord is going to descend into the tangent line. So we've got a little bit of work to calculate, let's see, this portion of the limit over here that I'm putting this blue box around. So let's get to that calculation now. And the start of that calculation is, and we start that calculation by looking at the following observation. And that comes from the fact that L epsilon and R epsilon are intersection points of the curve and the chord. But that means that L epsilon and R epsilon are roots of the polynomial, which is, well, essentially the function minus the chord. So we've got f of x minus c1x minus epsilon. But then I'm going to factor out or multiply this whole thing by 1 over cn, so I have a monic polynomial. And then, well, at this point I can expand this back out, and I'll have x to the n plus cn minus 1 over cn x to the n all the way down to, let's see, it's going to be c2 over cn x squared minus epsilon over cn. Notice I've gotten rid of my x term. Okay, cool. But then let's maybe give this thing a name. So we'll give this thing the name g of x. And then let's also note that since we know that L epsilon and R epsilon are roots of this, that means that we can factor x minus L epsilon and x minus R epsilon out of, well, this polynomial. So then we're going to be left with a polynomial of degree n minus 2, and it's going to be a monic polynomial of degree n minus 2. In other words, a polynomial with a leading coefficient of 1. So it goes xn minus 2 plus dn minus 3, xn minus 3, all the way down to, let's see, we're going to have d sub 0 would be maybe the constant term. And I guess it's important to notice that these d's are going to depend on epsilon. So maybe I won't put the epsilon dependence in there, but they most definitely depend on epsilon, because this factorization, whenever we change epsilon, we change this L epsilon and R epsilon, and thus those d's also have to change. So let's keep that in mind as well. And now, well, observe that we can look at this polynomial, which is the same as this polynomial. Think about the multiplication out of these polynomials and comparing coefficients, and we'll see the following. So let's see that cn minus 1 over cn is pretty obviously equal to dn minus 3 minus L epsilon minus R epsilon. And how do we get that? Well, that's the coefficient of, oh, that should be x to the n minus 1 over here. And then, well, the coefficient of x to the n minus 1 after we were to multiply that out. But then from there, we can see the following, and that is that the limit as epsilon goes to 0 of dn minus 3 is in fact just equal to cn minus 1 over cn. And we see that because L epsilon and R epsilon both limit to 0 as epsilon goes to 0 based off of, well, the picture up here, but then how we chose them as well. And now, well, now you can make a very, very similar argument using just comparison of coefficients, and that's going to lead you to this more general statement, which says that the limit as epsilon goes to 0 of d sub k is equal to c sub k plus 2 over c sub n. So now let's take some of this information that we've got and see how that will take us to the end. Okay, so this is where we left off. Here's the equation that equates these two polynomials from which we extracted coefficients to get these kind of interesting relationships right here. Like the limit as epsilon goes to 0 from above of dk is ck plus 2 over cn. Now let's observe some other things that we can get from comparison of coefficients. So let's notice that the constant term on the left-hand side is L epsilon times R epsilon times D0. But then the constant term on the right-hand side is minus epsilon over Cn. Okay, so that's cool. We've got this thing for L epsilon times R epsilon. But then also, by noticing that there is no coefficient of x on the right-hand side, that means that the coefficient of x on the left-hand side must be equal to 0. We're able to gain the following equation, and that is L epsilon R epsilon times D1 equals L epsilon plus R epsilon times D0. So again, that's just what we get from equating the x term on the left-hand side to 0. But now let's observe at this point we can kind of smash these two things together and solve for L epsilon plus R epsilon, and we see that that's equal to minus epsilon over D1, or times D1, all over Cn times, let's see, that's going to be D naught squared. But this is good news, because before we wanted the limit of L epsilon plus R epsilon over epsilon, and now we see that that kind of object has a nice form. So let's see, if we take this limit as epsilon goes to 0 from above of, like I said, L epsilon plus R epsilon over epsilon, which was part of our calculation for our S0 number, we'll see that that's simply equal to negative the limit as epsilon goes to 0 from above of, we've got D1 over Cn times D0. So D1 over Cn times, like I said, D0, well, squared. But we've got this formula up here that we derived before by looking at coefficients. So that allows us to calculate this in its entirety. And we end up with something like this. We'll get minus C3 over Cn. So let's see, that's what's going on in the numerator. And then in the denominator, we'll have Cn times, let's see, that's going to be C2 over Cn quantity squared. Okay, cool. But from here, what we can do is put that together with our previous limit that defined S0, and we'll see that S0 is in fact equal to C1 minus 2C2 squared all over C3. Okay, nice. But now, remember, S0 was not the definition of aberrancy, but it did give us a quick path to get to the aberrancy of the function. And so now let's maybe apply that to get our final answer. Okay, so we found out that this number S0 was C1 minus 2C2 squared over C3, where those C's come from our function up here, which was a polynomial. But now we can use this formula that involved SC along with the slope in order to calculate the aberrancy. And in this case, we'll have, well, we called that A0, or AC more generally, but A0. So that's going to be equal to 1 over C1. Recall that the slope of the tangent here is C1, so that's why that's got a C1 in it, minus S0 all over 1 minus S0 over C1. But from here, what we can do is simply do a lot of symbolic manipulation, and you'll see what we end up with is C1 and then minus 1 plus C1 squared times C3 all over 2 times C2 squared. But the great thing about this is that the coefficients of the terms of a polynomial are directly related to the derivative of those polynomial evaluated at 0. So that means that we can exchange all of these coefficients with, different derivatives at 0. So this C1 is pretty clearly equal to the first derivative at 0. And then let's see, this C3, well, it's maybe not exactly the third derivative at 0, but it is up to a scalar. I'll let you think about what that scalar is. It's related to 3 factorial. But doing all of those, maybe replacements, we'll get f triple prime of 0 here times 1 plus, let's see, that's going to be f prime of 0 squared all over, so 3 times f double prime of 0 squared. So maybe to put it more generally, or in a form that looks like these formulas over here, we would have this nice formula for the aberrancy of y prime minus y triple prime times 1 plus y prime squared over, let's see, all of that is over y double prime squared. Okay, so there you have it. We've just answered a question that I think a lot of calculus students probably think about after they learn about the geometric interpretations or implications of the first and second derivative. And this at least somewhat explains the geometry behind the third derivative. And that's a good place to stop.